Okay, last video of the week. This is section 7.1 on finding the areas between curves. And okay, I gave just 3 problems, but honestly, these problems take a long time, or they can take a long time. So let's do one problem now. 13. Well, it has 2 parts, part A and part B. But both of them are asking you to do the same thing, which is to find the area enclosed by these 2 curves. They give you a picture in the book, but in case there had been no picture, I will now do this whole thing out. This is what you have to do to find the area between these 2 curves. Well, you have to know all the things, and in particular, you should be comfortable with the x equals 4 minus y squared curve. What is it? Well, it's a sideways parabola. We learned this in pre-calc C. And what is x equals y minus 2? It's just going to be a line. And maybe you even want to just convert this line into y equals x plus 2, just for ease of drawing. And x is going to be 4 minus y squared. So what does that look like? Well, it's a parabola whose leading coefficient is negative, so it's going to be, this is a sideways parabola, but it's going to be opening left. When x is 0, when y is 0, x will be 4. So we're going to have some kind of thing that's going to be looking like that. Okay, so with that kind of background knowledge, let's get ready to graph this. Before we graph it, maybe we need to solve for the points of intersection, so maybe let's do that now so we can graph it accurately. Well, when do these 2 curves intersect each other? You have to do this to do the problem. Well, when does 4 minus y squared equal y minus 2? Okay, this is now just some kind of quadratic equation. We can just do this. We get y squared plus y minus 6. If I did that right, I did. And so that's y plus 3, y minus 2, and so, yeah, that's just right. So it's when y is negative 3 or 2. And I guess when y is negative 3, x will be negative 5, and when y is 2, x will be 0. Okay, so I'm now ready, kind of finally or something, to make a graph of this. I guess I'll just do it up over here. So let's go. So it's 1, 2, 3, 4. I know I have a point here. I know that there are going to be y-intercepts at 0 and 2. This is me sort of graphing the parabola in my mind, but I also know that I have this point out at negative 5. I'm going to have this point negative 3, and also they meet here. So okay, so what do I have here? I guess I have something like this, something like that. That's pretty good. That's my parabola, and sure it is. 1, 1, 4, 2, yeah. Okay, so then there's the line. The line is the line just y equals x plus 2, so it's just going to be the line with slope 2. It's going to go, with slope 1, and it's just going to look like that. I have already previously calculated with algebra. So okay, so there's some considerable amount of time and effort that's required to draw all this out, to solve for the points of intersection, and to figure out even what region it is that we're trying to find the area of. But alright, now that we've done all that kind of pre-calc, then I guess we're ready to go. Task, find the area of all this green stuff. And I know they provided this picture for you in the book, but they didn't tell you what these points of intersection were. So, okay. Well, here's where it gets kind of hard, because if you try to draw your rectangles vertically, you are going to be sad. Because, well, if you try to draw some vertical rectangles and you try to describe the dimensions of those vertical rectangles, so here's the red, and here you think of this as kind of an arbitrarily chosen x value somewhere, then what you see is that the length of that representative rectangle is going to be determined by the difference in heights between the line and the parabola. But once you move into positive x territory, then that's just no longer true. Now the representative rectangle is bounded on both the top and the bottom by the parabola. And so now we're really sad. And okay, that's why the good way to do this problem is not to do it like that. The good way to do this problem is to do it horizontally. If you split this this region up into a bunch of thin horizontal strips, then I can say with confidence that every single one of these horizontal strips is going to be bounded on the left by the line and on the right by the parabola. Okay, and so let's do it. The problem actually says to do it sort of both ways. So their language, I think, was with respect to x and with respect to y. So if we're going to do it with respect to x, which I consider to be the not good way or something, then I'm talking about the red vertical vertical rectangles. Okay, so one thing that gets kind of tricky is that these equations were originally given to me as this is the curve x equals 4 minus y squared, and this was given to me as the curve x equals y minus 2. But having the curves presented to me in x equals format, then it's already kind of suggesting that the better way to think about these curves is as sideways curves. And so perhaps I'll just do the part B first, or because that to me is more natural. What are we really doing? Well, this point down here is -5, 3, so the lowest y-coordinate is -3, and the highest y-coordinate is 2. And so I don't want to mess up this picture too much, but what we're really doing is we're partitioning the y-axis up into subintervals from -3 to 2. And so we're going to take the integral from -3 to 2. And what are we summing up? We're summing up an infinite number of infinitely thin horizontal rectangles. And what can I say about those horizontal rectangles? Well, the way these curves work is you're going to give me some y value, and I have these formulas which tell me what the x coordinate is. And maybe some people find this kind of helpful if you put a sort of dot right there. Well, what's the coordinate of that point? If you give me an arbitrary y value, then the coordinates of that point are 4 minus y squared, comma, y. In other words, the very equation x equals 4 minus y squared you should think of as basically telling you, hey, you give me a y, and I will output what the x coordinate is of the point on that curve. Maybe this is obvious. And this point over here is going to have x coordinate y minus 2. In other words, you plug in, you give me a y, and this line, this formula x equals y minus 2 spits out the x coordinate of the point on this curve. And so if you do all of this kind of labeling and notation, well now, I think it's clear that, oh boy, okay, it's clear what the length of that blue rectangle is. It's the difference in the x coordinates. And so it's going to be 4 minus y squared, the right endpoint, minus y minus 2. And if you think about it kind of strategically like this, then that formula stays true even when, for example, that blue rectangle is very small, and down here, even when it's regardless of whether 4 minus y squared is positive or negative, it's still always just going to be the difference in those x coordinates. Okay, that's the length of the blue rectangle, and now we multiply by the thickness of it. Alright, so one of those infinitesimally thin rectangles has length 4 minus y squared minus y minus 2, and has thickness dy, and I add up the infinite number of them from -3 to 2. Alright, that was a lot of work, and I still haven't done this integral yet. What is this integral? Well, it's the integral from -3 to 2 of, cleaning this up a little bit, negative y squared minus y, and then plus 6 dy. And you might think, okay, well, at least this is a polynomial. Alright, well, but it's still some, there's still some work to do here. So now we anti-differentiate this polynomial. We get negative y cubed over 3 minus y squared over 2 plus 6y. And all of that needs to now get evaluated at 2 and -3. And so, okay, what do I get? I'm going to get, when I plug in 2, I'm going to get -8/3. When I plug in 2 here, I'm going to get -2, and I'm going to get 12. Minus, what happens when I plug in -3? -3 cubed is -27, but then there's a negative, so 27, so it's 9. And then that becomes minus 9/2, and then minus 18. Whew, this is hard. Okay, -8/3, it's plus 10. Let's see, what do I get? Minus 9 plus 9/2 plus 18. So what's all that crap? That's 18 minus, that's 9. So it's 19 minus 8/3 plus 9/2. This can't be right, but it might be. I guess I need this all in terms of sixths. So, well, I'm just going to leave this 19 for a second. But this is minus 14 sixths, and this is plus, yikes, plus 27 sixths. What am I talking about? Multiply by 3 over 3, yeah. So that's 13 sixths. So this is 19 plus 13 sixths. So that's 20 and 5 sixths. I don't know why I'm suddenly doing mixed numbers, but this is 125 over 6 is my hope. My hope is that that is the right answer. I'm going to tell you in one second, and yeah, it is the right answer. Okay, oh my gosh, so much arithmetic, so much algebra, so many negatives, so many parentheses, anti-differentiation, integration, drawing of pictures, thinking, blah, 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 blah. That was only half the problem. The other half of the problem said, hey, do this whole problem over again, but now do it the bad way. Okay, so, well, I want to at least talk about the bad way for a minute. What makes the bad way a bad way is that I think this is just less efficient because we have to do 2 integrals. And in particular, I need now I need some new formulas, because this curve or line x equals y minus 2 is appropriate if you're integrating horizontally, but if you're integrating vertically, it's inappropriate. So I need to rewrite this curve as y equals x plus 2, because now I want to know sort of how tall these rectangles are. And gets kind of hard because I also need to rephrase this curve x equals 4 minus y squared as a y equals curve. And if you just sort of try to do like algebra 1 or whatever, you do have to be kind of careful, because if you want to solve for y, alright, you get y squared equals 4 minus x, sure. But then when you take the square root, you really need to allow for plus or minus root 4 minus x. And in fact, both of those are like relevant, right? This curve, the top half of the parabola, is really like the y equals root 4 minus x curve, whereas this curve down here is really like the y equals negative root 4 minus x curve. Okay, so finally, I'm ready to sort of talk about how you would set this up if you were going to do it horizontally. And the answer is, you now think of the interval that you're going to partition as going from -5 all the way to 4. All the way to 4, sure. And you're partitioning it up into subintervals. But really, I have to do one integral from -5 to 0. And I'm going to take all the x values from -5 to 0. And if you give me an arbitrary x, then I am going to construct this representative rectangle. And what are the dimensions of this representative rectangle? Well, they're the difference in the y coordinates between these two curves. And so the top curve is always x plus 2, and the bottom curve is going to be negative root 4 minus x. And then I need to add to this like a whole nother integral, which is the integral on the right hand side with this parabolic region. I can also just do this whatever. Now if you give me a number between 0 and 4, then it's going to be the representative rectangle is this red one, which is like root 4 minus x minus root 4 minus x. So then I get the integral from 0 to 4 of root 4 minus x minus negative root 4 minus x is one way of thinking about it. Okay, so if I'm going to really do this, I kind of just don't want to, but I get two integrals. The integral from -5 to 0 of x plus 2 plus root 4 minus x dx. And this becomes twice the integral from 0 to 4 of root 4 minus x dx. Okay, and I either want to just not do this and just trust that I do in fact get 125/6, or do it with doing a lot of things in my head because I'm getting sad. So let's do it in my head version. So this is x squared over 2 plus 2x plus. I'm gonna break all the Rowe's rules and just anti-differentiate this in my head. Oh man, I'm kind of losing it. It's like 1 in the morning. What is the integral of root 4 minus x? I guess it's gonna be like, I need to go up a power to 3/2. So it's gonna be minus 2/3 4 minus x to the 3/2. That might be right. Let's double check it. So to get a boom, negative, back inside negative. Yeah, that's just right. So evaluated at -5 and 0. And then over here it's going to be kind of the same thing, right? So this is going to be 2 times negative 2/3 or whatever. So this is going to be negative 4/3 4 minus x to the 3/2, but evaluated at 4 and 0. Okay, cha. Do I really want to do this? I mean, it's pretty clear that I don't want to do this, but I'm going to do it for you guys. So let's go. When you plug in a 0 here, you get 0, 0, but this isn't quite 0. This is 4 minus 0 is 4. 4 to the 3/2 is 8. So I get negative 16/3. Okay, so that's negative 16/3 is what I get for when x is 0, minus, what do I get when x is -5? Well, I get 25/2 minus 10. When x is -5, 4 minus -5 is 9. 9 to the 3/2 is 27. But then divided by 3 is 9, so I get minus 18. Okay, and over here, I'm going to get 4/3 times. Well, when x is 4, I get 0, but when x is 0, I get 4 to the 3 halves, which is 8. So, this is negative 16 thirds minus 25 halves. It's negative, so it becomes plus 28. And then this becomes plus 32 thirds. Yikes! So, what does all this become? This becomes 28 minus 25 halves plus 16 thirds. I'm gonna do some kind of, I don't know what I'm gonna do. What should I do? I guess this is like, I guess one way to think about this is, oh my god. So this is 28, that's like 12 and a half, right? So it's minus 12 minus a half, and then that's plus 16 thirds is like 5 plus a third. Okay, so I'm just going to do it that way because I know okay, so 28 minus 12 is 16 and 5 is 21. So this is 21, but then negative a half and a third. Well, a half minus a third is a sixth. So that's going to be minus 1/6. And so indeed I get 20, if you follow that. 1/3 minus a half is negative a sixth, so this is a sixth less than 21. So this is in fact 20 and 5/6. So I do get 125 over 6. Okay, I think you will agree that in this problem at least, it was terrible to do this horizontally, to do this vertically. It's better to choose the correct orientation to do your problems in so that you have only one integral to solve. And if that integral is just a polynomial, even better. Okay, I warned you this was going to kind of take forever. This one problem took me 22 minutes, and I was going basically as fast as I possibly could. Let's do 2 more problems and then call it a night and then call it a week. Whew, so much homework. 2 weeks of school left, that's it. That's it. You're mostly done. Try your best. Whatever you say, class. Don't say I didn't teach you calculus, because I did. I really did. Okay, 21. 21 now says, and now is where it starts getting hard when there's no picture, so you're just freaking on your own. Sketch the region bounded by the graphs of the algebraic functions and find the area of the region. Okay, so you're just given the functions and you just have to do it. So f of x equals x squared plus 2x plus 1. I know that guy. And g of x equals 3x plus 3. Okay, so once again, this is a sort of line and a parabola intersecting kind of a problem. Okay, so to make a picture, so we have to do, or maybe we set them equal to each other first to solve for the points of intersection, and then we'll know what kind of scale we need and stuff. So, alright, so that becomes x squared minus x minus 2. So that's x minus 2, x plus 1, so that's just right. So x equals 2 and negative 1. And when x is 2, y is 8. No, oh my god, 6 and 3, 9. What? Okay, 4 and 4, yeah, 9. And when x is negative 1, y is 0. Okay, so if I really want to do this problem, I guess I'm just gonna, yeah. Okay, I'll do my picture over here. What's happening? Well, okay, this is just really like x plus 1 quantity squared. So that's just a parabola moved 1 to the left. So it's going to look like this. And by the time I get to 0, it'll be up here at 1. But by the time I get to 2, it's going to be way up here at 9. So that's that. 2 comma 9. And anyway, there's my parabola. I guess. It's a pretty terrible parabola. Hold on. Sure. Okay, and then according to my math, that's also where these two lines intersect. That's where the line intersects. Is that reasonable? Let's see. That's 1, 2, 3. The line y equals 3x plus 3 has y-intercept 3 and slope 3. So yeah, over 2 up 6 and down 3 over 1. So what we have is this kind of a situation. I don't think I've ever actually done this problem before. Therefore, the region we're finding the area of is this sort of slender little region here, bounded by this line and this parabola. Okay, so draw like careful graphs, label your points of intersection, label this point is -1, 0, label your curves as well. What is this curve? It's y equals x squared plus x plus 2x plus 1 rather. And what's this curve? It's y equals 3x plus 3. And now I need to find the area of this curve. Well, what's the best way to find the area of this curve? I think it is to slice everything vertically. And so I'm now going to draw my so-called representative rectangle. And the representative rectangle looks like this. And why do I call this a representative rectangle? Because for arbitrarily chosen x value from -1 to 2, I can express the height of this rectangle as the difference in the y coordinates between the line and the parabola. And so what I'm really going to do is I'm going to partition the x-axis from -1 to 2, and I'm going to then add up all the sums of all these rectangles. So I integrate from -1 to 2, and the thing I'm adding up is the area of that little red rectangle. And what's the area of that little red rectangle? Well, for an arbitrarily chosen x, the top of that little red rectangle is 3x plus 3, and the bottom of it is the height of what I get when I plug x into the parabola. So minus x squared plus 2x plus 1. This expression represents the height of that rectangle, and if I multiply by dx, I get the area of that little rectangle, and then I add up the infinite number of them to get the area of the region. Okay, now I just have this integral to solve, and I guess I'll better do it, right? So I get -x squared, 3x minus 2x is just plus x, and 3 minus 1 is plus 2. Alright, so maybe now this won't be so hard. I just do it. -x cubed over 3 plus x, 2 plus x. Oh, one of these guys again. So that's -8/3 plus 2 plus 4 minus, I'm going to plug in -1. I'm going to get positive 1/3. And I'm going to plug -1 here, I get plus 1/2 minus 2. So this is still kind of a drag. -8/3 plus 6 minus 1/3 minus 1/2 plus 2. So that is 8 minus 9/3, so minus 3, which is 5, minus 1/2. So I guess the answer is 9/2. Is that right? It is right. Whew. Okay, one more problem to go for the week. Let's do it. Problem's not going to do itself. 27. 27 says, same directions. Here are my curves. F of y equals y squared, the book says, and g of y equals y plus 2. Okay, this is just the same freaking problem again, and I don't like this language. I'm just going to think of it as x equals y squared and x equals y plus 2. So what is this? This is just another sideways situation. When does y squared equal y plus 2? Well, when y squared minus y minus 2 is 0, y minus 2, y plus 1. So when y is 2 and negative 1, and when when y is 2, x will be 4, and when y is negative 1, x will be 1. Alright, so making a picture of this situation over here, I have 1, negative 1, and I have, sorry, what's going on? Oh, and 4, 2, cha, 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 cha. And why does this look so bad? X equals y squared. Oh, because I just was being dumb for a second. So yeah, the x equals y squared parabola looks like that, of course. And then x equals y plus 2 is really like y equals x minus 2. So that's the line that's coming like this. So that's why this is the situation. Check. Okay, so after much thinking and drawing and all this other kind of stuff, I've determined that this is the region that I'm trying to find the area of. It's the region that is enclosed between, on the one hand, the curve x equals y squared, and on the other hand, the curve x equals y plus 2. And the relevant points of intersection are this one, 1, negative 1, and this one up here, 4, 2. Okay, so this is really just another example of the problems we've already done. How can I find the area of this region? Since these curves were presented to me in like x equals form, it suggests that maybe I should think of them as being sort of sideways curves, and I think that's just better, right? Hopefully you see that partitioning these curves horizontally is just like the way to go here. Because if you partition this region up into horizontal rectangles, then every one of these rectangles has the property that its right endpoint is a point on the line, and its left endpoint is a point on the parabola. And so now the skill you have to sort of get good at is you have to, and I think a use of curly braces is kind of nice, right? You have to sort of have this kind of conversation where you say to yourself, okay, I am choosing an arbitrary y value. And that arbitrary y value is going to go somewhere